In this segment, we cover initial and boundary value problems. Generally, it's a very big area, but we are talking about initial boundary value problems in the context of ordinary differential equations. So let's basically define these two types of problems and then look at the techniques of solving them. Suppose you have dy by dx plus p of x into y is equal to q of x given y of x naught is equal to y naught. Or some d square y by dx squared plus p of x into dy by dx plus q of x into y is equal to r of x given y of x naught is equal to y naught and y dash x naught is equal to some z naught. These are examples of initial value problems because the conditions are specified at only one location of x. Therefore, these are initial value problems. On the other hand, if you look at a boundary value problem, an example could be d square y by dx squared plus p of x dy by dx plus q of x into y is equal to r of x given y of x naught is equal to y naught and y of x1 is equal to y1. Of course, several other boundary value problems are there, but in the simplest case, these can be understood as initial and boundary value problems. A boundary value problem will have conditions specified at two different or three different locations depending upon the order of the differential equation. So now the question is, if such problems are given, how do you find the solution for y? The idea is there are two possible ways of approaching such problems. One is known as the classical method and one is known as the transform method. By transform method, we invariably mean the Laplace transform method. In the next few illustrations, I am going to show you how a problem can be recognized as initial or boundary value problem and whether we should apply a classical method or a transform method. Question number 1. With initial condition x of 1 is equal to 0.5, the solution of the differential equation t into dx by dt plus x is equal to t is, the options are x is equal to t minus half, x is equal to t square minus half, x is equal to t square by 2 and x is equal to t by 2. Now let's look at this equation. This is a first order differential equation. Obviously only one condition is specified, therefore it can be treated as an initial value problem. Now how do you look at this problem? There are no difficulties about using a classical method. How do you know whether we should use a classical method or a transform method? Suppose the right hand side functions involve some discontinuous functions. For example, the unit step function or the impulse function, then the classical methods will fail. So you can go for Laplace transform methods in those cases. But this is free of any delta functions or the step functions. Therefore, we can take up the classical method. So let's look at this equation. This is dx by dt plus 1 by t into x is equal to 1. This is obtained by dividing the whole equation by t. So this is a linear in x. So the integration factor is e power integral 1 by t dt, which is e power log t or t. The solution will be x into the integration factor is equal to the right hand side function into integration factor dt plus constant. So xt is equal to integral 1 into t is t dt plus constant. So xt is equal to t square by 2 plus constant. It only remains that we should calculate c from the initial condition. So when t is equal to 1, x is 0.5. That's the meaning of that notation. So I will use x is equal to half and t is equal to 1. So half into 1 is equal to half plus c, therefore c is equal to 0. So under this condition, the value of the arbitrary constant is 0. So substitute that c is equal to 0 here. You will get xt is equal to t square by 2 or x is equal to t by 2. So this is the particular solution of this initial value problem, and you can see option D is correct for this problem. Question number 2. For the differential equation d square x by dt squared plus 6 dx by dt plus 8x is equal to 0 with initial conditions x of 0 is equal to 1 and dx by dt at t is equal to 0 is 0, the solution is, the options are x of t is equal to 2 e power minus 6t minus e power minus 2t, x of t is equal to 2 e power minus 2t minus e power minus 4t, x of t is equal to minus e power minus 6t plus 2 e power minus 4t, and x of t is equal to e power minus 2t plus 2 e power minus 4t. So he's already said initial conditions. We also can understand its initial value problem because both the conditions t is equal to 0 is specified. Right. Now let us look at this equation. This is a second order differential equation with constant coefficients, and the right hand side is a simple 0, so it is called homogeneous. Therefore the classical method is sufficient. So let us write the equation in the notation form. If you factorize, you will get d is equal to minus 2 or minus 4. So the complementary function is a e power minus 2t plus b e power minus 4t, because the roots are real and distinct, and the particular integral, because of the 0 right hand side, will be 0. Therefore x of t is equal to the sum of the complementary function in the particular integral a e power minus 2t plus b e power minus 4t. So we will have to apply these two conditions in order to derive a and b. The second condition requires that we differentiate this solution form, and we will have minus 2a e power minus 2t minus 4b e power minus 4t. Okay, we will call this 2. X of 0 is equal to 1 can be applied on equation number 1. X of 0 is equal to 1, when you apply, you will get a e power 0 plus b e power 0 is equal to 1, therefore a plus b is equal to 1. Similarly, the second condition can be applied on this. So when you apply this on the derivative solution, minus 2a e power 0 minus 4b e power 0 is equal to 0. So we will have a plus 2b is equal to 0. So we can say a is equal to minus 2b. So if you combine these two, you will have minus 2b minus b, that is minus b is equal to 1 or b is equal to minus 1, which means a is equal to 2. So you take a is equal to 2 and b is equal to minus 1 and substitute in 1, because this stands for the solution. So from 1, x of t is equal to 2 e power minus 2t minus e power minus 4t. This is a solution to the problem corresponding to option B. Question number 3. The solution of the first order differential equation x dash t is equal to minus 3x of t given x of 0 is equal to x naught is. The options are x of t is equal to x naught e power minus 3t, x of t is equal to x naught e power minus 3, x of t is equal to x naught e power 1 by 3, and x of t is x naught e power minus 1. So this is a very simple first order differential equation. X dash t divided by x of t is equal to minus 3. So this is a separable equation. So when you integrate, so you'll get log x of t is equal to minus 3t plus c. So x of t is equal to e power minus 3t plus c, of which e power c can be called a new constant a, e power minus 3t. So we only have to estimate the parameter a from this initial condition. X of 0 is equal to x naught implies you will have to substitute t is equal to 0 and equate the solution to x naught. So you will have a e power 0 is equal to x naught, e power 0 is 1, so a is equal to x naught. Substitute this parameter in equation 1 and you will have x of t is equal to x naught e power minus 3t. This is the solution and the correct option is A. Question number 4. For the equation x double dash t plus 3x dash t plus 2x of t is equal to 5, the solution x of t approaches which of the following values as t tends to infinity? The options are 0, 5 by 2, 5 and 10. Now this equation is a differential equation of second order with constant coefficients. Right hand side is a constant, therefore classical method will be enough. So if you put this in notation, d square plus 3d plus 2 operated on x of t is equal to 5. So when you factorize this part, you will get d is equal to minus 1 or minus 2. So the complementary function will be a e power minus t plus b e power minus 2t. Now comes the particular integral, which is 1 upon d square plus 3d plus 2 operated on the constant 5, which can be written as 5 times e power 0t. So using the principles of finding out the particular integral, a substitution d is equal to 0 should be sufficient. So xp is equal to, this will be 5 by 2, because this is 0, this is 0. So the complete solution will be x of t is equal to xc plus xp. This is nothing but a e power minus t plus b e power minus 2t plus 5 by 2. This is only a general solution. No initial conditions or boundary conditions have been specified. But the question is, what happens to x of t as t tends to infinity? As t tends to infinity, you get a e power minus infinity plus b e power minus infinity plus 5 by 2. Both of these are 0, so you get 5 by 2. So this is nothing but the steady state value of the function, and this corresponds to option C. Question number 5. The solution of the differential equation dy by dx is equal to ky given y of 0 is equal to c is. Again, there is nothing much in this problem. It's a separable equation. Dy by y is equal to k times dx. Integrate, which you can compactly write as y is equal to a e power kx. In fact, we can write this as y of x is equal to. So let us apply that condition. Y of 0 is equal to c. So you get a e power 0 is equal to c. So a is equal to c. So use this value in the solution and you will get y of x is equal to c e power kx, which corresponds to option C. Question number 6. A function n of x satisfies the differential equation d square nx by dx squared minus nx by L squared is equal to 0 where L is a constant. The boundary conditions are n of 0 is equal to k and n of infinity is equal to 0. Then the solution of the equation is, the options are k e power x by L, k e power minus x by root L, k square e power minus x by L, and k e power minus x by L. There is another equation which has got constant coefficients with a 0 right hand side. So the classical method is sufficient. If you put it in the standard notation, d square minus 1 by L squared into n of x is equal to 0. So if you solve for d, it will be plus or minus 1 by L. So therefore, n of x is equal to a e power 1 by Lx plus b e power minus 1 by Lx. And the particular integral is 0, therefore this is the solution. But then it's a boundary value problem, you can see. Therefore, you will have to determine a and b under those two conditions. Suppose you consider n of 0 is equal to k. So, we will put x is equal to 0 in the solution and then equate the value to k. So, you will get a e power 0 plus b e power 0 is equal to k. Therefore, a plus b is equal to k. Let us invoke n of infinity is equal to 0 in equation number 1. So, this becomes a e power infinity plus b e power minus infinity is equal to 0. E power infinity is minus infinity is 0 and it takes away b along with it. So, you still have a e power infinity is equal to 0 because this has become 0. But e power infinity is so large it cannot be 0. This implies a is equal to 0. Put a is equal to 0 here and you will get b is equal to k. So, a is equal to 0, b is equal to k may be substituted here and you will get n of x is equal to, a is equal to 0 means this term is not there, b is k e power minus 1 by L x. Option D for this problem is correct option. Question number 7. The solution of the differential equation k square d square y by dx squared is equal to y minus y2 under the boundary conditions y is equal to y1 at x is equal to 0 and y is equal to y2 at x is equal to infinity, where k, y1 and y2 are constants is. There are 4 options: y minus y1 into e power minus x by k square plus y2, y2 minus y1 into e power minus x by k plus y1, y1 minus y2 sine hyperbolic x by k plus y1, and y1 minus y2 e power minus x by k plus y2. So let's look at this equation. It's a second order differential equation. It is already specified that k, y2 and y1 are all constants. So let's write this equation as k square d square y by dx squared minus y is equal to minus y2, d square y by dx squared minus 1 by k square y is equal to minus y2 by k squared. This right hand side is a constant. So put this in the standard form. And solve for d, you will get the complementary function a e power 1 by kx plus b e power minus 1 by kx. Because of a non-zero right hand side, you need to calculate even the particular integral. So 1 by d square minus 1 by k squared operated on minus y2 by k squared e power 0x. This is a constant, therefore d is equal to 0 should be sufficient to substitute. So therefore you will get 1 by minus 1 by k squared into minus y2 by k squared. K square will get cancelled and you will get y2. Therefore y of x is equal to the complementary function plus particular integral a e power x by k plus b e power minus x by k plus y2. So this is a general solution where the parameters a and b have to be determined from the two boundary conditions. Now let us look at the first condition, y is equal to y1 at x is equal to 0. So you put x is equal to 0 and equate this to y1. So you will get a e power 0 plus b e power 0 plus y2 is equal to y1. So you can say a plus b is equal to y1 minus y2. For our convenience, we will call this equation 1. Now, we have another condition at infinity. At x is equal to infinity, y is equal to y2. Let us substitute in equation 1. You get a e power infinity plus b e power minus infinity plus y2 is equal to y2. So these two will get cancelled. E power minus infinity is 0. So a e power infinity is 0. Because e power infinity cannot be 0, a is equal to 0. When a is 0, we can calculate b. b will be y1 minus y2. Now you finally take a is equal to 0, b is equal to y1 minus y2 and substitute in equation 1. So y of x is equal to, this is not there, y1 minus y2 e power minus x by k plus y2. So this corresponds to option D. Question number 8. For the differential equation d square y by dx squared plus k square y is equal to 0, the boundary conditions are y is equal to 0 for x is equal to 0 and y is equal to 0 for x is equal to a. The form of the non-zero solutions of y where m varies over all integers are, the options are summation am sin m pi x by a, summation am cos m pi x by a, summation am x power m pi by a, and summation am e power m pi x by a. Now let us look at this equation. D square plus k square into y is equal to 0. So you get imaginary roots. So y of x is equal to c1 cos kx plus c2 sin kx, which are harmonics. Now we will have to find out the constants c1 and c2 from the given conditions. Let us call this 1. So when you apply the first condition, y is equal to 0 at x is equal to 0, so you will get c1 cos 0 is 1 plus c2 sin 0 is 0, therefore you get c1 is equal to 0. So in the final solution, this term will disappear. Then y is 0 for x is equal to a. Let us apply this again in this condition. So you will get c1 cos ka plus c2 sin ka is equal to 0. But already c1 is 0, therefore c2 sin ka is equal to 0. Both are candidates to become 0, but if you make c2 is equal to 0 and already c1 is equal to 0, the solution will always be 0. Therefore c2 cannot be 0, which implies sin ka is equal to 0, and this we can write as sin n pi. So k is equal to n pi by a, or in the problem instead of n he is using m. So k is equal to m pi by a, where m is greater than or equal to 1. We are writing this because sine is a periodic function. Therefore, y of x, I am writing now this from equation number 1. So C1 is not there, 0, and instead of C2, we can put am sine k is m pi by a into x. Remember, m takes values from 1 to infinity. Therefore, a solution like this will be forming the non-zero solution of the differential equation. Such things are very, very common in the context of solving differential equations using Fourier series. So the correct option for this problem is A. Question number 9. Consider the differential equation d square by dt squared plus 2 dy by dt plus y of t is equal to delta t with the conditions y of t is equal to minus 2 as t tends to 0 minus and dy by dt is equal to 0 as t tends to 0 minus. The numerical value of dy by dt as t tends to 0 plus is. Now this is an interesting problem because of the right hand side. Because it's a delta function, you cannot apply the classical method, but you can only go for the Laplace transform method. Laplace transform method is particularly effective when you have discontinuous right hand side functions. So just like delta t, which is a spike, you can also have unit step functions and other discontinuous functions. Okay, so we apply Laplace transform technique. Already in an earlier segment on Laplace transforms, we had seen all these things. So let us put it in notation: Laplace of y double dash t plus 2 times Laplace of y dash t plus Laplace of y of t is equal to Laplace of delta of t. Of course, you must know all these rules. S squared into y of s minus s y of 0 minus y dash 0 plus 2 times s into y of s minus y of 0 plus y of s, and Laplace of the delta function is 1. That is very, very important to understand. Now we can use these two conditions here, here and here. So we'll have s squared y of s, y of 0 is minus 2, so this becomes plus 2s, this is 0, plus 2 times s into y of s plus 2 is equal to 1. So the transfer function y of s can be derived. Of course, we have one more y of s here. So what happens, we'll have 2s plus 1 and all the other terms can be sent to the right hand side. So what are all the things which can go? 2s goes to the right hand side, minus 2s, then 4 goes to the right hand side, 1 minus 4 is minus 3. So this is what we get. So y of s is equal to minus of 2s plus 3 by s plus 1 whole squared, because this is a perfect square. So we can write this as minus of 2 into s plus 1 plus 1 by s plus 1 whole squared. So this will be minus of 2 by s plus 1 plus 1 by s plus 1 whole squared. So this is y of s. Now what is that we want? We want dy by dt as t tends to 0 plus. So what we can do is, if you take the inverse transform of this, y of t is inverse transform of y of s, that you can easily write minus of 2 e power minus t plus t e power minus t. Y dash t is equal to minus of minus 2 e power minus t plus e power minus t minus t e power minus t. Now we want y dash t is equal to 0 plus, and therefore this becomes 2 e power 0 plus, rather minus e power 0 plus 0. So 2 minus 1 is 1, and the correct option for this problem is A. Question number 10. A solution for the differential equation x dot t plus 2xt is equal to delta t with initial condition x of 0 minus is equal to 0 is, options are e power minus 2t into u of t, e power 2t into u of t, e power minus t into u of t, e power t into u of t. Again in this problem, a delta t on the right hand side indicates you cannot use classical methods, you must go for the Laplace transform method. Among other things, x dot t means dx by dt, so it is nothing but x dash t plus 2 times Laplace of x of t is equal to Laplace of the delta function. So this will be s into y of s minus y of 0 plus 2 times x of s, make it x of s and x of 0 is equal to 1. So s plus 2 into x of s, x of 0 is equal to 0 can be taken, so that it vanishes, and you will have x of s is equal to 1 by s plus 2. So if you want a solution of this, you must take the inverse transform of this transfer function. So the inverse transform of 1 by s plus 2 can be written as e power minus 2t into the unit step function. So the correct option for this problem is A.